Okay, so for the homework, the problems are given to you in a certain order. Maybe some of the earlier problems on the assignment or some of the problems from an earlier homework assignment could be useful for this one. So if there's one that you're particularly stuck on, number 17a maybe something earlier in the homework assignment might shed some light on 17a. Okay? Maybe not. There's multiple ways to do a lot of these problems. And that's one of the things that makes the subject so interesting, is you have several different paths to get to the answer. Okay, so again, let me know when you want the exam to be. I will say definitely sometime today to talk about just in generalities some of the problems and some of the hints. The review session will be today at around 5:30 in Mission. Kayla decided that we're going to walk to Mission today from the Children's Center. She's technically decided we're going to jog to the Children's Center. I am not quite sure what a 4-year-old jog will look like, but we should hopefully be there sometime around 5:30, a little bit after. Possibly with a giant stuffed dog. Okay, so what I want to do today is I want to prove a theorem in the book that has one step, I think, that they don't really go into too much detail there, that they kind of glossed over one small fact. And so I want to just go through the proof a little bit more carefully and try to highlight that point. And then I want to talk about the argument principle. And the argument principle turns out to be one of the most useful ideas in complex analysis. It relates certain integrals to the number of zeros and poles. And from that we get Rouché's theorem. And from Rouché's theorem we get the open mapping theorem. And from the open mapping theorem we have the max modulus. So you can kind of see now why we're talking about spin-offs from sitcoms. Lots of spin-offs from the argument principle. There's just so many great results it has. And what's your intuition about these results versus their analogs in real analysis?
There aren't any.
There aren't any, right. As always, we have extremely different behavior with our complex functions. Okay, so the first is talking about behavior of functions at infinity. So I don't want to go into too much detail about this, but I want to talk a little bit about what's going on. So unfortunately, the complex plane, there's lots of different ways it looks like to go to infinity. But a really good way to understand what's going on is let's let big F of z equal f of 1 over z. And so now, if I want to understand the behavior of my function little f at infinity, that's understanding the behavior of this related function at 0. So I pass from having to understand things at infinity to having to understand things at 0. Why is this worth doing? We have a good theory of understanding what's going on at finite points. And so we say big little f has a removable singularity, a pole, or an essential singularity if at infinity if big F does. So basically we just reduce the understanding of what's going on at infinity to understanding what's going on at 0 for this related function. We're not going to do it in too much detail, but there is the one-point compactification of the complex plane. And a nice way to visualize this requires some drawing skills, unfortunately. So if you have a really good imagination, this is supposed to be a sphere with a plane cutting through it. If your imagination isn't that good, this is my token sphere for today. Here's the plane cutting through it. Okay? You choose a special point on the sphere, the North Pole, okay, or the South Pole, either way, and then what you do is you draw a line connecting your point to some point on the plane. And so if I go over here, I choose some point on the surface of the sphere, I draw a line from here, and I'll hit somewhere in the plane. If I choose a point in the lower hemisphere and I draw through it, I'll get some point in the interior of the plane. So basically, if I look at the plane, here's the cross-section. All the points in here are from the lower hemisphere. And all the points up here are from the upper hemisphere. And this gives you essentially a one-to-one correspondence between points on this complex plane and points on the sphere. There's one point on the sphere that we miss. Yes?
I'm sorry, how are we choosing what point on the plane corresponds to...
Well, I draw a straight line from the North Pole to any point on the surface of the sphere and look and see where does it hit in the plane. So if I choose a point in the bottom, so for instance, let's say I choose the South Pole, I go straight down, I get the point 0. If I choose actually any point on the great circle in the XY, in the complex plane, I actually just get back the XY plane. If I choose any point in the upper hemisphere, I get a point outside the unit circle.
Okay.
There's one point I miss.
The North Pole.
The North Pole. So when you look at it, it maps the complex plane to a sphere minus a point. Can you think of a way to compactify the image by adding just one point? So it maps the complex plane to the whole sphere except for the North Pole. What one point could I add on the sphere to compactify it?
The North Pole.
The North Pole. What do you think the North Pole should correspond to? Infinity. Right. So if you actually blow up this flag, that's what it says. Okay? What's really going on is you should really view the North Pole as infinity. This is a really nice way of viewing what's going on. If you look at any path of points that goes off to infinity in the complex plane, and you look at the image on the sphere, it's getting closer and closer and closer to the North Pole. This becomes a really great way of viewing what's going on. Okay? If you, of course, have better artistic talents than this. Okay? So we're not going to do too much with that, but I just wanted you to be at least aware of its existence. So the theorem I want to prove is the following. Actually, I need one definition first. We say F is meromorphic on the extended complex plane if it has finitely many poles and no essential singularities. So in particular, it can't have an essential singularity at infinity. It has at worst a pole at infinity. Notice I'm saying poles but not removable singularities. Why am I not allowing it to have removable singularities? The name is the answer. We just remove them. Right? So if there's removable singularities, we remove them. Right? So really the only dangers are when we have poles. The book doesn't really emphasize why we assume only finitely many. What would go wrong if we had infinitely many poles? I'm sorry?
It gets weird when we integrate.
Well, we're not integrating right now. I'm just... If I give you an infinite set, what must that infinite set do? And this is where it might be nice to view it as a compact sphere. So if I give you infinitely many points on a compact set, what must happen? It accumulates. There has to be a subsequence that converges. Now my subsequence that converges could be at infinity, but I'm not talking about the extended plane. I'm allowing myself to understand the behavior at infinity. If I have infinitely many poles, they have to accumulate somewhere. And then it turns out, well, if you have infinitely many poles and something accumulates, wild things will happen.
By extended complex plane, are you referring to what you were just talking about?
I'm basically referring to, I also want to talk about the behavior of my function at infinity. Okay, so I'm allowing myself to consider the behavior of the function at infinity. If you want, view it as now the complex plane is now the compactified sphere, where I've added the North Pole. So a lot of times, I mentioned, I think, Picard's theorem, not the Picard maneuver, Picard's theorem that if I have a function that misses 2 points, it's constant. There's a generalization of this to the extended complex plane, where essentially now you add infinity. Okay? So here's the theorem. F is meromorphic on extended complex plane implies F is a ratio of polynomials, i.e. it's rational. I just realized probably writing i.e. is not good in complex analysis. Alright. So if you're a meromorphic function on the extended complex plane, then you're actually a rational polynomial. You're a ratio of 2 polynomials. This is a really nice classification of such functions. Okay? So the question is, let's try to think of some functions that are meromorphic. Well, if I give you the function e to the z, that has no poles. But e to the z is definitely not the ratio of 2 polynomials. What goes wrong?
An essential singularity.
Good. Goes wrong with e to the z. Essential singularity ad infinitum. And that's the problem. So we will see for many things later on that if you have no zeros or poles, you can be written as the exponential of a holomorphic function in many cases. And this is going to be an extremely useful result in many subjects like number theory. What we're trying to do now is we're trying to classify what functions can exist with certain properties. And so here's the proof. Say the poles are z1, z2, zn, and maybe z infinity. So at each pole, let's write f of z as f k of z plus principal part of z. So here, what we're doing is we're taking our Taylor series. These are all the negative terms. So this is principal series, the negative terms. Since I have a pole, can I have infinitely many negative terms? No. So we can write pk of z is going to be a to the negative n sub k over z minus zk to the n sub k plus dot 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 plus a I'm going to prevent the notation from being overloaded too much. Okay, to negative 1 over z minus zk. So if you look at this, it's going to look like a polynomial in z over a polynomial in z. Right? So again, whenever I have a function like this, I've got to have some number of negative terms, and then what's left over is going to be nice. What do we know about the degree of this polynomial relative to this polynomial? Do they have the same degree? Is the numerator larger degree? Is the denominator larger degree?
Denominator.
Okay, how much is the denominator larger by?
By 1.
By 1. So denominator degree equals numerator degree plus 1.
Oh, yeah.
Yes.
I got it.
Right. Okay, so this is what's going on at any of these finite poles. Now the question is what's going on at infinity, right? So I have to then figure out what's the behavior like. Now, the question is, of course, is this a useful thing to do? What am I trying to do? I'm trying to show my function is a ratio of rational polynomials. Right, I've got ratios of polynomials coming out over here. This is a good piece to have in the decomposition. So now I want to continue this decomposition and move it on to what's going on at infinity. So study behavior at infinity. So the book uses, a two-step notation, which is a little bit confusing at first. F of 1 over z is big F of z, and they write that as f tilde of z, and we'll put it infinity there, plus p infinity tilde of z. And essentially what we're doing here, essentially is a bad word to use in this. What we are basically doing here is say, well look, if I want to understand my behavior at infinity, that's the same as understanding the behavior of this related function. And now I've passed it to understanding what's going on at 0. I still have to give a name to my function. I could put the name of 0 here, but it's much better to use infinity because it's really coming from understanding my original function at infinity. And so what they now do is they now go backwards and say f of z is f, I want to make sure, I think it's just f infinity, right. I'm missing something here. One over z, I think I got a typo in notes. Plus p infinity. Okay. And this is now going to describe what's going on in the limit. So I now study this new function, h of z is f of z minus p infinity. I think they prefer to write it like this. Doesn't really matter. Where f infinity of z is f tilde infinity of 1 over z. It's just passing the behavior around as to where do I want to look at things. Sum k goes from 0 to n of p k of z. All right, let's look at this function. What can you tell me about the behavior of this function near one of the poles, say near z1? Does this function have a pole at z1, or is this function nice at z1? So what's the behavior of this function near z1? Pole or no pole? What did we subtract off from this? We subtracted off the principal part coming from the pole at z1. There's no longer a pole at z1. The rest of the stuff, these are just nice polynomials. If I put in z1 over here, and I have z2 over here, z1 minus z2 is not 0. This is well behaved as long as z does not equal zk.
Does it apply to all the poles?
So this function no longer has any poles. So removed all poles. That's nice. Well, what about at infinity? We've also fixed the behavior at infinity. So there are no poles anywhere. Okay? Now we have a function that has no poles. Do we know anything else about this function? What fact would you love to know about this function? So that we could use some of our results.
Holomorphic?
Well, okay, we do have holomorphic. So that does give us all the integration results. But we can do something without integrating. There's a really nice result that if we knew one more fact about this function, we would know what it is.
If it missed 2 points.
Okay, so one thing is if it missed 2 points. But if we're trying to prove that it's a rational function, we're not going to be able to get missing 2 points. It's a good thing to try, but there would be too many possibilities.
You mean it's bounded?
If it's bounded. So if the function is bounded, then it has to be constant. And then if it's constant, well, all of these are polynomials and we just move things over and we're fine. So all we have to do is show that it's bounded. Well, if you look at what's going on, the behavior at infinity is now nice. So it is bounded. Therefore constant. And so the reason is, if you think back to what's going on at big F, that's analyzing the behavior near z goes to 0. So we've subtracted off the pole at infinity. So if you look at what's going on, here's big F. Here's z equals 0. And in the neighborhood of z equals 0, everything is well behaved. So take a circle of radius epsilon about 0. Everything is well behaved. Is the function bounded in this disk? Yeah, it's a finite disk, finite area, finite radius. Function is holomorphic. It's bounded. What does this correspond to with the function little f? Well, here's 0. Not quite drawn to scale. What's the radius of that circle? Not infinity. 1 over epsilon, right? So all the points inside the circle of radius epsilon for big F is the same, and no, this is not a bright star, is all the points outside a circle of radius 1 over epsilon. So what I've shown is, if I look at what's going on in the complex plane, away from outside of the circle of radius 1 over epsilon, it's bounded. Inside the circle of radius 1 over epsilon, it's bounded because it has no poles. So now we know the function is constant. Okay? So this is the key thing to realize, is that if you take a small neighborhood of infinity, that's equivalent to taking a disk of very large radius and looking at all the points outside. And that's what we're doing here. So we have a complete classification. So all you have to do now is just collect and do some algebra and see that this will give you a rational polynomial. Each one of these only goes so many terms. And so when you multiply everything out, you will get a polynomial. So big part of complex analysis is, how well can I classify things? What can I say about the functions that have a given property? And the reason this turns out to be so useful is, when we start studying your number theoretic systems, or maybe sometimes in physics systems, you have some idea of the properties of the system. And that will give you information as to what it looks like. One of the things we're going to do is we're going to skip chapter 4 for now. After we finish chapter 3, we're going to move on to chapter 5, to Weierstrass infinite product. And it turns out you can write sine as an infinite product. And there's a unique way to do this. And what's nice about stuff like this is it allows us to use a lot of very powerful techniques to understand these functions. Okay. So I want to at least state the argument principle, and then maybe state Rouchet, Open, and Max, and then you use the rest of the time to just talk about some of the homework problems. Because it seems like there were a couple of questions from the stuff this week. Okay. So the first is the argument principle. What's really going on, as you've read the book, is there's not a great way to define the logarithm and keep all the properties we want. So for real numbers, what's some of your favorite log properties?
The exponent, like the log of e, the log of inverse of e.
Okay, so the log of something to a power is that power times the log of the number. That's a nice one. There's another nice property that I really like. And my probability students should have this as a Pavlovian response.
You can move it in limits.
Not limits. Nice properties of logs that I love from probability. Why do I always want to take logs in probability? Log of a product is the sum of the logs. Right? We no longer have that with complex numbers. And so if I give you the log of r e to the I theta, we'll talk about this in great detail. It seems natural to say, well, this should be the log of r plus I theta.
But you have to.
Well, the problem is
theta.
I can keep changing theta. I can add 2 pi to theta without changing the number. So it turns out there is no unique way to define the logarithm on all of C. What we're going to see in section 6 is what we have to do is we have to take a cut of C and throw away a nice curve going off to infinity. And once we do that, we can define the logarithm. The typical damage we normally do is we normally throw away the negative real axis. And if you throw away the negative real axis, well, if I start here, I can't go all the way around and get back to where I was. I can't go around 2 pi radians. You could, of course, instead maybe try to throw away some kind of strange spiral like this. I urge you not to throw away strange spirals like this. It's very nice to just throw away a line. And so in section 6, we will look at something like this. So sadly, one of the key properties that we want the logarithm to have fails. Okay? So maybe complex analysis is not the ultimate perfection. There's a few things that sadly get it. But even though this fails, there is a related property that's important that does hold. If I give you f1, f2, derivative over f1, f2, this is f1 prime over f1 plus f2 prime over f2. And what's nice about this is just the product rule. f1 prime f2 plus f2 plus f1 f2 prime. The f2's cancel here, then the f1's cancel. So we still have something like this. So if I want to try to integrate something like this, I can break it up into simpler integrals. So I'm very big on Pavlovian responses. When you see something, there are certain instinctive things you should do. In complex analysis, you want to integrate functions. One of the functions you want to integrate is the logarithmic derivative. So if I give you g of z is the log of f of z, and yes, I know we haven't defined what log means, and we know that there's problems defining log. Forget about that for a moment. G prime of z, what's the derivative of log of f of z? If you just pretend you can do everything correctly.
F prime over F.
Is f prime of z over f of z. This is called the logarithmic derivative. Not surprisingly, of f. And so whenever you see things of the form f prime over f, what you're really doing is that's really the derivative of a log. And the entire subject of integration comes down to the fact that the antiderivative of 1 over x is log of x. This is why complex analysis works. This is why we get all this stuff. That's the big idea. So what I want to do now is look at some very interesting logarithmic derivatives. So can somebody give me a good function to look at for logarithmic derivative?
Log Z.
No, we don't even know what log z is. I want a simple function.
Z.
Z. I'm going to make it a little bit more general and make it a z to the n. Because it's really not that much harder to do this than to just do n equals 1. So f prime of z is a n z to the n minus 1. So f prime of z over f of z is going to be a n z to the n minus 1 over a z to the n. It's just n over z. What's nice about this is if n is positive, this is essentially the number of zeros divided by z. If n is negative, it's the order of the pole divided by z. So n positive, we have number of zeros divided by z. If n is negative, we have the order of the pole divided by z. What's the remaining case? And if n equals 0, 0. And 0 gets 0. Well, okay, let's see. If n is 0, what we're doing is we're taking the derivative of a constant. Yes, I'm not surprised that the derivative of a constant is 0. What this is telling us is the action happens at the zeros and the poles. And this logarithmic derivative captures the action. All right, well, rather than looking at the function a z to the n, what could we look at next? We could have more terms. And so what I want to do now is say, well, let's say we have a more general expansion. And so more generally, we could have the following. Let's let f of z be a z to the n 1 plus g of z, where g of z is holomorphic. So what I'm basically doing is I'm taking my Taylor series and I'm just pulling out the first non-zero thing. Okay? So if n is negative, this is still going to be holomorphic. If n is negative 5, then when I multiply by this, my next term will be the negative 4 term. If n is positive, if n is 8, the next term will be the 9th term. Okay? Let's calculate f prime of z. So how do we calculate f prime of z?
Split it up.
Yeah, split up. Don't use the product rule. Right? Take it as two different terms, but unfortunately when you split it up, you'll have oh, okay. And a to the z to the n minus 1. Now we need the derivative of that times g of z, so it'll be a and z to the n minus 1 g of z plus a z to the n g prime of z. So that should be the derivative of f. Now, if I look at f prime of z over f of z, what will I get? I'll get n a to the z to the n minus 1. There's a couple of ways to write the algebra. I'll write it this way. I'm going to group these two terms together as 1 plus g of z divided by a z to the n 1 plus g of z. Now over here I get a z to the n g prime of z over a z to the n 1 plus g of z. All right, well, if I look over here, I have cancellation galore, right? And I'm left with n over z. And now for the next one, I'm left with g prime of z over 1 plus g of z. But remember, g of z starts off as, b z plus dot, dot, dot. Why doesn't g of z have a constant term? So this is extremely important. Why does g not have a constant term? I pulled out the z to the n term, right? If g of z had a constant term, if it started off 3 plus something, well, I should incorporate that here. That would change the a that I pull out. So it has to start off with a z, otherwise it's the same size, it's the same order. What can you tell me about this function? So I've got g prime of z over 1 plus g of z, where this is a multiple of z.
Z? Or
Which one?
negative Z? If you could, that'd be
Well,
G measure.
We don't know what the coefficients are. We just know that g is a multiple of z. Can the denominator be 0? Yeah. What if z is really small? Can the denominator be 0? If z is really small, could 1 plus g of z vanish?
No.
No, because this is a multiple of z. Think of z as like epsilon. So this is holomorphic if z is small. And this is a polar. So when we integrate, if we integrate this along a closed curve, what will we get if we integrate this? We'll get 0. So when we integrate this, we'll get 0. When we integrate this along a closed curve, we should get like 2 pi I n. Okay? And so now we're ready to state the argument principle. And this is essentially going to be the proof. Is when I break things up like this, integrals of this piece aren't going to matter. They're not going to contribute. Everything always comes down, when we do integrals in complex analysis, to, where are the poles? Okay, so argument principle. F is meromorphic in open omega, finitely many poles and zeros. C, a circle in omega, no poles or zeros on the circle C. Then 1 over 2 pi I, the integral over C of f prime of z over f of z dz is the number of zeros inside C minus the number of poles inside C. And this is called the argument principle. And this is one of the most useful things you can do, is to integrate essentially the logarithmic derivative. So when we talk about the Riemann zeta function later this semester, this will be a huge way to prove the prime number theorem. And it'll be relating information about the primes to information of zeros of the Riemann zeta function. The proof is essentially the calculation we've seen time and time again. We've just shown that whenever we have f prime of z over f of z, it looks locally like this near a zero or a pole. And if I'm away from a zero pole, nothing really matters. And so the proof is the following. You take your circle, you take the finitely many places where it has a zero or pole. And as always, we draw a little contours coming in like this. So I'm not going to go through the whole rigmarole of having the little bands going to 0. I'm just going to go straight to, we have a bunch of small circles about each of these. And then integrating on the outside is the same as summing the integrals over all of these. And then for each one of these, we can expand it like this. If we're sufficiently small, these pieces don't contribute. And this piece, what do we get when we integrate? 1 over 2 pi I n over z dz. The n comes out, and we just get n. And so notice all the zeros count positively because their n is positive. All the poles count negatively. So really, the minus sign is just reflecting the fact that it's just the sum of all of these. Okay? So the proof is in the book. It's also in the notes that I have for the class. It's the same proof we've seen again and again. The whole key to the proof is this formula over here, that near a zero or pole zk, f of z looks like n over z minus zk plus g prime of k of z over 1 plus gk of z. And since this part is holomorphic, its integral will be 0. This part will give us exactly what we need. Okay. Any questions on the argument principle? Okay. So now that we have the argument principle, I want to just state 3 quick consequences of the argument principle, which we will then prove in detail on the first non-mountain day after today. And so I'm going to just quickly state them. Consequences of argument principle. The first is Rouchet. C, unit circle, holomorphic in omega, which contains C, Fg, holomorphic with the absolute value of f greater than the absolute value of g on circle, then the number of zeros of f in C equals the number of zeros of f plus g in C.
So what's homomorphic?
F and g are holomorphic. So I'm giving you two holomorphic functions, and I'm telling you the absolute value of f is strictly greater than the absolute value of g on the unit circle. And of course, there's nothing special about the unit circle. We can do this for other regions as well. The next is the open mapping theorem. If f is holomorphic and u is open, then I won't say this out loud, but the image is open. Okay? So the image of an open set is open. And the last is the maximum modulus principle. Gamma is a simple closed curve, f holomorphic in omega, which contains the curve gamma. Then the maximum of the absolute value of f occurs on the maximum value of f for all z on or inside gamma occurs on the boundary, i.e. gamma. What this means is I have some nice region omega. I have some curve gamma. It doesn't intersect itself. It divides the plane into two regions, an inside and an outside. And I want to know, where is the absolute value of f largest? The absolute value of f is largest at some point on the boundary. That doesn't mean it's largest there and nowhere else. It could be as large there and many other places on the boundary. It could also be maybe that large inside the region. But the maximum must occur on the boundary. Okay? And with a little bit of work, if the function is non-constant, I believe that the maximum can only occur on the boundary. So if I take my function to be constant, then yes, I have lots of places where the function is largest. And what we'll see next non-mountain day is argument implies Richet, implies open mapping, implies max modulus. So in terms of why we care about stuff like this, this allows us to identify where a function is largest. And at least one of your homework problems will crucially use this fact to try to understand the behavior. Okay, so I wanted to leave the last 5 minutes to just talk about some of the homework problems. So if there's any homework problem that people have been looking at and stuck on and would like to discuss a little bit, let me know, and I'm happy to spend a few minutes. Yes?
I was just confused, like for number 5, sort of what is going on in the denominator.
Okay, is this 5 on page 103? Okay. Okay, so this is the contour integral one, right?
Yeah.
So we're integrating e to the minus 2 pi I x c over 1 plus x squared squared. Alright, so we have e to the negative 2 pi I x c over 1 plus x squared squared. Okay. And so they tell you what this is supposed to equal. So the question is, what contour do you want to use? So are there any dangers for this as x goes through real values?
Real values?
For real values, no. So we don't have to worry about taking a detour about the origin. So we could either use a rectangle or a semicircle. We use this if c is greater than 0. And we use this if c is less than 0.
And why do we do that?
Well, what would happen if, let's look at the function. So f of z, our first guess, is e to the negative 2 pi I z c over 1 plus z squared squared. When z is large, I'm going to look like essentially 1 over z to the 4th. So I'm going to have lots of decay on the semicircle. The length of the semicircle is only r. I've got like an r to the 4th down below. I'm happy. But the problem is this exponential factor. And so if I write z as x plus iy, we get e to the negative 2 pi I xc. E now I times I is minus 1. Right? That reinforces the minus sign there. Or maybe I got it backwards. 2 pi yc over 1 plus z squared squared. So I think I have this backwards. I think we want to do it this way. So if y is positive, I have exponential growth, which is very dangerous. So if I have c is greater than 0, I want to go and use this contour.
So that you avoid the growth.
So that I avoid the growth. And then the question is, where are the poles of the function? So where is 1 plus z squared 0?
Negative I.
Negative I and positive I. So each of these contours will include a pole. Now, if you think about this, you really only have to do one, because if you take the complex conjugate of this, if you replace c with negative c, oh, sorry. Oh, wait, can we, no, I can't turn the camera on you. If you send x to negative x, that's essentially the same as replacing c with negative c. You only have to do one. Or if you think about what's going on, if you think of this in terms of cosine and sine, if c is negative c, it's the odd part, it's going to be 0 anyway. So you might as well assume c is either positive or negative, whichever way you want. So the trick for this one is figuring out which contour to look at. And we have decay like 1 over r to the 4th from the denominator, but we have to make sure we don't have exponential growth in the numerator. Okay. Other things to discuss from the homework. 17. So 17 will hopefully make a little bit more sense now that we're getting these results. But, you know, again, you're supposed to have already read this for today's class. You're supposed to have finished reading these sections. So just so you have a sense of how well you're preparing. It's not the same just reading the material as getting the lecture. We'll talk about this in more detail, which is one of the reasons I'm happy to push 17A down. 17A is the hardest problem, I think, on the exam. So this is the homework. This is the one where the function has absolute value 1 on the boundary. One of the things I would love to do for this problem, but I haven't been able to make it work, is to say, well, can I prove that it maps the unit disk, so it maps the perimeter to the perimeter? Do I at least go all the way around? If I know that, I think I can prove it. But the problem is, maybe when I map this, maybe I start going like this and I come back like this. And I get into all these topological nightmares. So I can give you some hints. So I think it's 11:50 now. So if anybody wants to leave, by all means feel free to leave. I'm happy to stay in chat for a few more minutes. If you don't want to hear the hint, this is your chance to leave. Think 15D. Now, I'm going to actually give you an incorrect hint as well. And I'm not going to tell you which of the hints is correct. Look at z over f of z. F of z over z. 1 over f of z. So at least one of these 4 things is a good hint. And no, I will not give you a hint on what is a good hint. So at least one of these is a good thing. But these are good things to potentially look at. For 17, I tell you the function has absolute value 1 on the unit circle. What can you tell me about this function? So if f has absolute value 1 on the unit circle, what's true about z over f of z?
Absolute value z.
Which is?
Not good.
No, but absolute value of z is what on the unit circle?
Oh,
1. What about f of z over z? What about 1 over f of z? So here are 3 other functions to try to apply the maximum modulus principle to. Right? Now, I might have some issues looking at z over f of z, or f of z over z, or 1 over f of z. I need my function to be non-zero, otherwise this is not holomorphic. But the whole point in problem 17 is asking you, prove that every point is hit. Let's assume it doesn't hit 0. If it doesn't hit 0, now 1 over f of z is well-defined and holomorphic in the disk. So that's now a function to look at. So these are good things to try. And again, I'm not saying which one of these will work. There's at least 2 different ways to prove 17. Okay. Craig, do you want to say goodbye to Umang?
Yes. Bye.